Hello everyone. In this video, we're going to talk about binomial distribution and examples involving binomial random variables. So the brief outline, we'll look at 5 examples, start out with a couple easy ones, take a look at a few moderate examples, and then we'll take a look at an extension example. So suppose there's a multiple choice exam with 3 possible answers for each of 5 questions. What's the probability that a student will get 4 or more correct by just guessing? And let's round this off to 4 decimal places. So 4 or more correct by guessing. So we're interested in the cases where they get 4 correct and 5 correct out of the 5 questions. So let's start by letting x be the number of correct answers. That's our random variable. X is a binomial random variable and is 5, and p is 1/3. We want to find p of 4 plus p of 5. So we have to think in terms of our PMF, or the formula for calculating a binomial probability. Probability of 4 is 5 choose 4, 1/3 to the 4th, times 2/3. This would be to the first power, but I omitted that since we don't need it. And then we add 5 choose 5, that value is just 1, times 1/3 to the 5th power. Okay, if we work this out and then round off, our final answer should be 0.0453. So that's example 1. Example 2. Let's suppose that in a US Open tennis match, a player hits an ace once out of every 5 serves. Suppose also that the player will perform 80 serves over a certain period. So first question, what is the expected number of aces? And then we follow that up with what is the variance and standard deviation number of aces? Well, if we think about the situation, a player either hits an ace or doesn't when they serve. We know that when we let x be the number of aces, x would be a binomial random variable. And there's a very easy formula for finding the expected value for a binomial random variable. It's just n times p, and that's what we have here. 80 serves gives us n is 80. There's a 20% chance that the serve is an ace, right? Because they're hitting an ace 1 out of every 5, so 20% chance. So this tells us that the expected number of aces would be 16. To find the variance, we have another easy formula for a binomial. It's n times p times 1 minus p. So we multiply these values out and we would get 12.8. And then the standard deviation for the number of aces would just be the square root of the variance. So square root of 12.8 is 3.5777. That concludes example 2. Now in example 3, let's suppose that you randomly text 20 of your friends to see who wants to go on a hiking trip. You think they'll all respond to your request independently of each other, and you estimate that each one has a 7% probability to be available, interested in going hiking, and will actually text you back accepting the invitation. So in other words, a 7% chance they will say yes. You're asked to find the probability that at least 3 people would accept the invitation and find the expected number and variance of people who would accept the invitation. So this is a good example where I would suggest stop the video right now and try to solve the problem. Okay? It's not terribly easy. I would call this a moderate problem, but it's more towards the easy side than the hard side. Okay, so if we start talking about the solution, let's let X be the number of friends that accept. Notice X would be a binomial random variable, N would be 20, and P would be 0.07. 7% chance that they would accept. So we want to find the probability that 3 or more accept. Well, we could find this using the complement. So this would be equal to 1 minus the probability X is less than or equal to 2. And we'll think of this as 1 minus the probability X is 0, minus the probability X is 1, minus the probability X is 2. So to get these three probabilities, we have to use the PMF. And you can see here we have the probability, let's say X is 0, would be 22 0 times 0.07 to the 0, 0.93 to the 20th. Here's the probability X is 1, and then the probability X is 2. When we work all of these out, these three probabilities, they should come out to 0.8390. And then we subtract that from 1. So our final answer for part A is 0.1610. So about a 16% chance 3 or more friends will accept. Now in part B, we wanted to find the expected number. So again, we use the formula n times p. N is 20, p 0.07. We would get 1.4. And the variance, n times p times 1 minus p. So we're multiplying really 1.4 times 0.93. We'll get 1.302. Okay, so that concludes example 3. Now example 4 has a new twist, and you'll see these in various binomial distribution problems. Suppose that 2% of secretaries know Excel. How many should we interview in order to have at least a 50% chance of getting one that knows Excel? All right, so we can model this type of question as a probability problem. Let's let n be the number of secretaries we decide to interview. Let's let X be the number among the n secretaries that know Excel. Then X would be binomial. N, right, that's the number of secretaries we decide to interview. That's sort of our unknown. In fact, that's what we're looking for. And P is 0.02 because we know 2% of the secretaries know Excel. So in terms of probabilities, we want to find N so that the probability that X is greater than or equal to 1 is greater than or equal to 0.5. Right? Okay. Remember, X is the number of secretaries that know Excel. So we want at least a 50% chance we find one that knows Excel. Okay, so if we start to express this in terms of parameters, we have the probability X greater than or equal to 1. Well, again, we think of this in terms of the complement. So 1 minus the probability X is equal to 0. So this would be 1 minus n choose 0, 0.02 to the 0 power, 1 minus 0.02 to the nth power. So simplifying a little bit, n to 0 is just 1, so we could omit that. 0.02 to the 0, again, that'll just be 1. Inside the parentheses here, I have 1 minus 0.02, so that gives me 0.98 to the power of n. Okay, so now we could think, well, we want to pick n so that this expression that we have here for the probability, 1 minus 0.98 to the n, is at least 0.5. Okay. Now notice here we can simplify this inequality a little bit. We could think of it in terms of, I bring this term, I have a negative sign, so I bring this over to the right side. I get 0.98 to the n on the right. And I subtract 0.5 from both sides. So I just have 0.5 left on the left. Okay, so now how do we solve this equation? I have an equation where my unknown is an exponent. Well, you may remember, okay, what we need to do is to take logs. So starting here with this inequality, I'll take the log of both sides. And this could be base 10 log. It could also work with the natural log, but there's no need to use that. We'll use the base 10 log. So I get the log of 0.5 is the log of 0.98 to the n. And there's a property of logs that let us move the exponent over. So I could write this as n times the log of 0.98. At this point, I'm just going to calculate these logs. Remember, the log of a number between 0 and 1 is negative. So the log of 0.5 ends up being minus 0.301. Log of 0.98 is minus 0.0088. All right, what I'm going to do next is just multiply through by -1 to get rid of the negative signs. But remember, when I multiply an inequality through by negative, I have to change the sign. So this becomes 0.301 less than or equal to n times 0.0088. And now we just solve for n by dividing by the 0.0088. So I divide both sides of the equation by that term. We get 0.301 over 0.0088 less than or equal to n. Or if I work out this fraction, we get a number about 34.32. Okay, n must be an integer, so this tells me that n needs to be at least 35. Okay, so that concludes example 4. One last example. This we're going to think of as an extension in a certain way. So suppose, despite lecturing roommates on energy conservation, there's a 60% chance the lights in a dorm room will be left on when nobody is there. Let's assume each day is independent. Suppose that for every day the light is left on in a dorm room, there's 1,000 watts of power used. But every day when the light is turned off, there's only 200 watts of power used. So you decide to keep track of, let's call it X, the number of days the lights are left on, and we're keeping track over the next 30 days. So you could see X would be a binomial random variable. The number of trials would be 30. And you could see that there's a 60% chance the lights will be left on. So 2 questions here. What's the expected amount of power used during the 30 days? And find an expression for the probability that 16,400 watts of power or more are used during the 30 days. So the answer to part A is fairly straightforward. There's 30 days, and 60% of the time the lights are left on. So we expect 18 days that the lights are left on. And since it's a 30-day period, that leaves 12 days the lights are turned off. So the expected power use would be 18 times the 1,000 watts a day when the lights are on, plus 12 times the 200 watts of power when the lights are not left on. So we could, work this out, and you'd see that this works out to be 20,400 watts. So that answers part A. Now part B is asking us for an expression. So here we have the probability, trying to calculate the probability. Number of watts is at least 16,400. So we have 1,000 plus 200 times 30 minus x greater than or equal to 16,400. And you can see right here that there's something missing. This should be 1,000x plus 200 times 30 minus x. So this concludes the video. I hope you've enjoyed it.